Okay, it is my pleasure to introduce the final invited speaker of LOGML 2021. He is Professor Martin Rumpf of the University of Bonn. He studies Riemannian calculus on shape spaces with applications in imaging and computer graphics. Today, he will talk about sparse principal component analysis on shape manifolds. Thank you, Martin.
Thanks a lot. It's a great pleasure to present here some work which we've done over the last couple of years. And in particular, I would like to convince you that Riemannian geometry, a fairly abstract concept, is really worth being considered if it's about real-time surface editing and character animation. The question is only how you define the shape spaces and how can you efficiently implement tools from Riemannian geometry and statistics. And this project has been supported by the NFF project, Geometry and Simulation, funded by the German Science Foundation and the Austrian Science Foundation. And for sure, there is support by the Haushoff Center for Mathematics at our university. Oops. So here's a teaser, what I'm going to present. So we have a lot of input data, and we will do a Riemannian sparse PGA. That is, we will group these input data into related classes, and then we will bundle these classes. This is what you see outlined here in color. So inside the bundles, there is a strong interaction of the different types of motion, of variation of the shapes. And in between these bundles, these groups, there is only a few interaction between the modes. And that is the key. Once we have this, then we can do deformation synthesis, mesh editing, and other animation purposes. What you see on the right is now an animation, where on top of it, you see for the whole sequence, color-coded with different colors for every mode, the contribution of this mode of variation to this animation. So this is in particular joint work with Klaus Hildebrandt from the TU Delft and Joshua Sassen from my group. And it is based on joint work with Chao Zhang, Bernd Heeren, and William Smith, and over the last couple of years. So what I'm going to show you is first how to really understand the space of triangulated surfaces as an implicit manifold. This will immediately incorporate rigid body motion invariance, as you will see, and this will incorporate also a nice locality principle if it comes to variations. Then we will learn about the Riemannian metric on these space of triangulated surfaces and develop a geodesic calculus, which consists of geodesics, logarithm, exponential map, Fréchet average, and covariant derivative, paratransport, and so on. And in particular, because we are heading for a sparse principal geometric analysis, Riemannian principal analysis, we will first review the principal geodesic analysis and then turn it into a sparse one. And that will allow us to approximate very efficiently and effectively a submanifold generated by all these modes, which we have computed via the sparse PGA, and allow us, because of the already briefly described separation of these mode groups, to an efficient deformation synthesis. So what is a triangulation? A triangulation for all of us is at first a set of vertices V, a set of edges, and a set of faces. And once we have the topology fixed, then the set of vertices leads to these R to the 3 times the number of vertices degrees of freedom. But there is another perspective onto triangulations with different set of variables. Namely, the variables are now all the edge lengths which can be computed based on the vertex positions, these L of x, and all the dihedral angles, which is sketched here below, at some edge, the angle between the adjacent facets. And thereby we can also describe a given triangulation. And it's very easy to see basically by spreading out the triangulation using this Li and theta I information to get to unique representation. But the problem is not all L theta vectors, which we from now on will call Z, represent really a triangular surface. So there are conditions which have to be fulfilled. The obvious first condition is just a triangle inequality, which is an inequality of this type. Tf of L is larger than 0, where Tf of L consists of these three terms here. And there is for each interior vertex, if our surface is of disk type, there is one closing condition. If you walk around the surface, if you walk around the point on the surface, then finally this fan of triangles has to close. And that is a condition which can easily be computed based on L and theta. And we express it in terms that the function Q for each interior vertex, depending on L and theta, vanishes. This function can very efficiently be computed based on quaternions. And in compact form, for this T-map, which gathers all these triangle inequalities of all faces, and for the Q-map, which gathers all these equalities for all interior vertices, we can express the manifold of triangulations as all those vectors in R to the 2 times the number of edges, where the triangle inequalities and this Q condition equals 0 are fulfilled. That is our manifold now. And the big advantage, which is obvious at first glance, is that if we do a rigid body motion, then all the vertex positions are rotated and translated, but the L and theta stay the same. That's immediately clear, and that's a core advantage. A manifold has a tangent space under smoothness conditions, which are fulfilled here. And because this is just an open condition here, and that is an implicit surface representation, we already know that the tangent space is just the kernel of the Jacobian of this Q-map. Now, these are all those Z-type vectors, variations of L and theta, which solve this equation here at some given Z, where we would like to define the tangent space. And here you see another big advantage. If you want to describe a variation of a surface, which looks like this here, then these deformations require large components in the deformation of all the vertex positions. In particular, actually, this hand is just transported. It's not really moving itself. Nevertheless, it's here equipped with a strong blue color indicating a strong deformation. Whereas the L and theta components of the same variation are much sparser and much more localized. Here you see there is indeed no component describing the motion, the non-existing deformation of the hand itself. There is only the component which does the turning of the arm and the stretching here, which is indicated by light blue and green over here. So if we want to measure length, then we need a metric to turn this manifold into a Riemannian manifold. How to do so? So the metric acts at a certain position on the manifold. This is the position Z. And you plug in, it's a quadratic form on the tangent space, so you plug in two tangent vectors. And the principle we follow here to define a metric is what is called Rayleigh's paradigm. We consider a deformation energy. Let's think of it as an elastic energy, where you also have infinitesimal variations. And then we compute the Hessian of this up to this factor 1/2. This defines us a metric if we replace displacements of this elastic energy or strains by strain rates. So that means we have here elastic energy to define, and we compute just the Hessian, and that is a very natural, very nice metric. So how to define this elastic energy? So we consider our surfaces, our triangular meshes, as discrete shells. In the discrete shell context, it's quite widespread that there are two types of deformation energies. One is internal distortion in a tangent space. That is what is also called membrane distortion. And then there is external bending of the surface. And for discrete surfaces, the bending energy can, for instance, be defined by considering a change here, a discrete change of the dihedral angle, theta e, that is really doing bending, yeah? Properly scaled so that we turn this into a discrete surface integral. And the membrane distortion, if you know a little bit about elasticity theory, then elastic energies usually depend on the Cauchy-Green strain tensor. That is what we have in this discrete context as well here. This is up to infinitesimal rotations, measuring really the in-plane deformation. And that can be scaled here with the area of the triangle to turn this again into a discrete area integral. This G is the Cauchy-Green strain tensor, and the membrane energy density can, for instance, be defined nicely as such here. There is the trace, there is the determinant popping up, and there's the log of the determinant of A. So you might wonder why we choose a nonlinear approach here. But the determinant is very practical, because if I have an admissible triangulation and a triangle is degenerating and getting closer to overfolding and thereby a lack of triangle inequality, then we see this membrane energy density tending to infinity. So that means using this energy, we automatically, once we are in the class of admissible triangulations, we stay in this class and we don't have to care about the triangular inequality condition. So now from Riemannian calculus, it's well known that the fundamental object is the path energy. So we have a path in the manifold and we want to compute a function on it. The most natural one is to integrate the metric on the motion velocity along that path. This is what you see here. That defines the path energy, a continuous path energy. And for fixed endpoints, Z0 and Z1, its minimizers are known to be geodesics. They also minimize the length of the curve. And they have, in addition, the nice property that they are parameterized with constant speed. So once we are able to compute geodesics, then we can compute the logarithm. If I have a geodesic from Z0 to Z1, this geodesic as a minimizer of the path length has an initial velocity Z.0, and that is just the definition of a logarithm. And the opposite, which is not a variation problem, but an ODE problem, if I start at Z0 with an initial velocity Z0, I can reconstruct, solving an ODE involving the covariant derivative, I can reconstruct the Z1. And what I end up with is then the exponential map. And as I already said, the square root of the path energy is the distance. And we can consider a couple of intermediate points equally distributed. Then the path energy splits into the sum over the squared distances due to the Cauchy-Schwarz inequality scaled with a factor k. And now we step from continuous geodesics to discrete geodesics, from continuous underlying path energy to discrete path energy. So if we think of this formula, which I've shown on the last slide, this distance here is really the remaining distance. It's complicated, too complicated to compute. So what we do is we just replace this up to higher order terms by a function which should be easy to compute, wz z tilde. Indeed, this function in our context is precisely the elastic energy which we've used to define the metric. It's at hand, it's easy to compute, it's easy to compute the derivatives of that. And then we look for that formula here and we replace the square distance by this second order approximation here by this w zk minus 1 zk. And this gives us a discrete indexed here with k path energy. And the picture you should have, if we think of an embedded surface in R3, then if we think of classical geometry on that surface, then this W could be just the squared embedded distance. So just the distance on the sphere, just the distance between the 2 points, zk minus 1 and zk squared. And then the W is nothing else but the spring energy. And the path energy is just a chain of springs which I try to relax on the surface under the constraint that all my points lie on that implicit surface. And that picture holds also in our case here because we are dealing with an implicit surface in very high dimension for sure, but and for sure not with the embedded distance in the Euclidean space, but with this physical distance based on the elastic energy. And discrete K geodesics are then defined as minimizer of the discrete path energy. And if we want to compute minimizers, then we have to solve the Lagrange equations. Degrees of freedom are all the intermediate points. The 0 and the k point are fixed because that's my variation problem. And each of those zk points appears in 2 of these w terms. One's paired with zk minus 1, and one's paired with zk plus 1. And that means the Lagrange equations are just a system for all the intermediate points of these equations. I vary the second argument, zk, in this term, and with respect to the first argument, this w, because here's the zk. And that's the system which we have to solve, for instance, by Newton's method. And then finally, we might not be on the surface precisely if we do some small step. So it might be necessary to project back onto this implicit surface. And that could be done by using the back projection involving really the remaining distance, but because our distances are very small here in all the applications we consider, we just use here this elastic energy, which was our approximation of the squared distance as the object which we minimize to figure out the nearest point, so to say, on the implicit surface, and that is called Z here. And that can be easily done with very few Gauss-Newton iterations to do this projection. which is sketched, for instance, here. From there, projecting down there. So now let's start discussing principal geodesic analysis. PCA, principal component analysis in Euclidean space, also with a scalar product, which might be different from the Euclidean scalar product, but a fixed one that's well known. And the principal geodesic analysis is just the translation to Riemannian manifolds and has been considered in many publications so far. The tools required for this is first, we need to compute a generalization of the mean. In this context, the mean on Riemannian manifolds, which is the Fréchet k-mean. We denote this by z bar. And this is computed just as the minimizer of the sum of squared Riemannian distances. And we have these Riemannian distances at n because we can approximate them with our k-geodesics in all directions. So you can think of this as a large spider of chains of springs, and we relax the whole spider. That gives us the geodesic, the Fréchet mean, the discrete Fréchet mean. And then the discrete logarithm, that's also near at hand. So we compute here between Z0 and Zk a discrete geodesic. This is indicated here by this polygonal path. And then this vector here in the embedding space from Z0 to Z1, that is somehow a tangent vector. It just has to be rescaled properly with k here. And it has really this vector to be, because an embedded vector and not a tangent vector, to project it onto the tangent space, which is easy to do with our implicit definition. And the discrete exponential map, which we need then for reconstruction purposes or animation purposes or editing purposes, there we proceed as follows. So we start with a discrete initial direction from Z0 to Z1. And then we take these set of Euler-Lagrange equations. We take the first one and solve it now involving Z0 and Z1 for the third point, Z2. And we do this iteratively. So we take, we solve this equation here. So we try to make this as close as possible to 0 here, solving really the Euler-Lagrange equation. And that defines us then, if I do this k times, uppercase k times the discrete exponential. And now what is the PGA algorithm? We first compute the mean as in the standard PCA case. Then we compute the logarithms of the input data, Zn. That turns these objects outside in space into tangent vectors, discrete tangent vector, for sure, Vn. And then we can combine tangent vectors and work with them. And this is possible if we then perform PCA in the tangent space, where the scalar product underlying this PCA is the metric, the length measurement representation on the tangent space. And thereby we, for instance, can compute uppercase J principal modes of variation in the tangent space. And mathematically, in a compact form, this leads to this optimization problem. So the V here is in rows, just the input data. Therefore, these are R to the 2 number of edges vectors, and we have then uppercase N of them. So the U's are now the PCA computed principal J first modes, dominant modes. And as usual in PCA, they are orthogonal. So that means paired in the metric, they give us the Kronecker. That is a constraint for this 2 number of edges times J matrix U. So in the rows of that matrix, we see the principal modes and we have J of them. And then the W matrix is just the weight matrix required to define the best approximation in this U basis of the G distance of the input data. And yeah, that is just the principal geodesic analysis in compact form. And this gives us J modes, U1 to Uj. And if we plug linear combinations of these modes into the exponential map, then we define a submanifold, a data representing submanifold of the shape the really very large shape manifold M of U. M, sorry. This is defined, this X at the Frisch mean applied to linear combinations of these U vectors defines this M of U as the submanifold. Be cautious. If we consider linear combinations and then apply the exponential map, that's far from first applying the exponential map to linear to scaled versions of the principal component vectors and then adding them. Because this is an addition in the tangent space, and this is an addition in the ambient space in which our manifold lies. PGA is much more robust than PCA plus orthogonal projection onto the manifold, which would, for instance, be your first guess. That is visualized here. So the green is the PGA. The dots indicate the precise position of a variation. And you see here the percentage with error less than this root mean square error listed here on the x-axis. And you see that we get with the PGA much earlier, very nice approximations than with the PCA, which is indicated by this strong defect, which you see over here. So let me make some remarks on this discrete calculus. So we first know for a very large class of these, including the class considered here, of these discrete path energies, that they gamma converge in the L2 topology to the continuous path energy. In particular, minimizers, due to equicoerciveness, also converge to discrete minimizers, converge to the continuous minimizer of the path energy. But we have even more. We have really H12 convergence of these minimizers. We have that the logarithm converges, which is an H1 infinity finite element estimate. And we have that the exponential map converges, which is an ODE estimate for an implicit ODE scheme. And in addition, which we will not need here, we also know that there is a discrete connection, discrete parallel transport, discrete splines, discrete curvature tensor, and they all can shown to converge nicely to their continuous counterparts. So here you see in experiments that we get a first order consistency experimentally. Here is with the relative error. Here are the number of points along the curves. Here is the error in the logarithm case, in the exponential map case, and in this combined case, and the triangles indicates first order convergence. And that has been performed on the SCAPE data set. So now we would like to make this PGA sparse. What does this mean? So the principal modes, they are orthogonal, and orthogonality is basically organized by balancing contributions with different signs, and the modes of a classical PCA and the classical PGA, they have large overlap. So we would like to have small overlap of these modes, because then we can nicely treat them in the L theta coordinate separately. And to this end, we consider now this variation problem. So here is the same term. V is the input data. U represents here the matrix. Those columns, are the principal modes, sparse modes in this case. W are the weights. And here are now of these modes L1 norms. This is the usual sparsity approach with some penalty factor lambda up front. And for sure, the UJs must be on the tangent space. For sure, now we don't require them to be orthogonal. That would contradict the sparsity. But then we have to do something, because if we don't assume anything in addition, then we can make these UJs small, the W's large. That leads to small L1 norm, but doesn't change the approximation quality. So that means we avoid that the W's get large just by imposing this constraint on the absolute value of the W's. And then in this L1 norm, it's not a good idea to use here just the L1 norm, the little L1 norm of all the components. In particular, the theta components have a completely different meaning than the edge-length components. So therefore, we think about physically suitable weightings. And for certain P norms here, we actually use only the 2 norm that reproduces our metric, and the P equals 1 norm, which leads to this weight which we require here. But we take the same factors which we already know from the metric. And that defines this 1 norm. So one obvious question is it really necessary to ensure that the UJs are tangential? It is, which is indicated by this example here. We take a variation with only theta components of this hand animation here. And if we then don't impose this here, then we locally see here immediate chaos in the triangulation, overlaps, and irregularities. And we see a strong loss in the approximation quality. That means this geometric nature of these variations, being in the tangent space of the Fisher mean, is indispensable. So now the question is how to solve this system. And I just would briefly describe how to do this. So there are the 2 variables, the matrix U, the matrix W. If you look for this problem with W, for giving U, it's easy. That's a sequentially quadratic program. And there are tons of algorithms to solve this. It's a little bit more tricky with the U, in particular because here is a green missing because of this L1 term here. So how to turn this into a sequential quadratic program? So we first look for this term here. So this G, Frobenius metric, that turns into this here if I spell it out. And G is here just the Hessian of W, which appeared in the definition of the metric. And then you basically multiply all this out and you get quite nice terms, and you can move the U. So you can move the W over here to make it even more handsome. And that's a nice quadratic energy. And then this here, the 1 norm, if I fill the matrix with rows, which are all equal, these weight factors corresponding to the corresponding index in these M coefficients, then I can write this term here in matrix notation just as the trace of these M transpose times the U matrix where we have converted every entry into its absolute value. That is just notation. Then we are left with this. There is a linear inequality that is the tangent space property. And there is this quadratic part here. And there is this non-quadratic part because of this absolute value here. And now we consider a relaxation. We introduce new variables, u plus and u minus. Under this constraint, u plus is positive and u minus, which play the role of minus the negative components, is also assumed to be component-wise positive or non-negative. And then, due to this inequality here, which is obvious, just a triangle inequality, we can estimate this term arising in the optimization problem by this term with these constraints. That would be a quadratic sequential program. And we just write it down here again. So now here we have this, the first term, this quadratic form. This is now split with u plus and u minus. The second term is also split with this. Here is now the linear, constraint, the tangent constraint. And these are now the inequality constraints, which are fairly easy. And the key point now is that equality and not inequality holds if and only if the components of u plus and u minus are disjoint. So that means if the u plus component is not zero, then the u minus component has to be zero and vice versa. That is expressed in compact form in this using this component-wise product here. But then it's clear that in our minimizer, this condition must be true. And hence equality must be true. And our relaxed problem is the original problem. That is because the only thing we change here is the regularization cost. And if we do not fulfill this property here, then we pay obviously a larger cost for the quadratic energy here. And that has to be avoided. And hence, here is really equality, and the relaxed problem, the solution of the relaxed problem is the solution of the original problem. And this problem here is a sequentially quadratic program. So now we have something which is sparse. So that means there is a strong preference, if any way possible, to have principal modes, principal sparse modes, which have disjoint or closely disjoint support. And now we assume that we can split our space of all principal components into subspaces which are pairwise strongly disjoint. Non-disjointness of sparse modes is then gathered in these subspaces. And because of this disjoint nature, if we have a UA and a UB from a disjoint subset here, then the exponential map can now indeed be nicely approximated by first computing the exponentials in the direction and then just summing the L and theta components. And for sure, this is always done relative to the mean position. Yeah? And here you see an example. There is a mode A, a mode B, and a mode C. You see that the mode A and the mode B are strongly separated. And the mode A and C have a very strong overlap. And because here this arm is moving and this arm is moving as for the mode A as well. So if we have now these components, we can take tangent vectors in these UI components and then compute, because of this separation, a reconstruction, Z of V, just computing the exponentials and then summing them properly up. And finally, in all our applications, then just jump over this little gap and project the Z of V, this uppercase Z of V, onto the implicit manifold. And that gives us our map, little Z of V. So here you see an experimental study. These are these ABCs. And if we look for A and B, and here we do different computations for different multiples of these modes, A and B, you see that they give a very nice reconstruction. The solid surface underneath is the exact solution. The point cloud is the solution obtained just by adding these L theta vectors resulting from shooting in different disjoint directions. That is completely different in the case where there is a strong overlap of the modes, which is indicated here. Here is mode A, mode C. So you see here a big error, exact reconstruction versus reconstruction just by shooting in the different directions and then just linear combination. So you can compute this discrepancy matrix of the results really shooted by the exponential, just computing the difference here with the exponential and then pairing them in the L2 norm divided by the norms of the separate shooting. This is definitely in between 0 and 1. Close to 1 means a very strong overlap. Close to 0 means very few overlap of these modes. And that is heat map colored over here. You see here some spots of strong overlaps of the mode. And you also see here that if we take a random mode, decompose it, and then color code here this error in the exponential, or this exponential component, then you see that there's a strong locality principle. If I start with this mode, and here we color the components actually of the mode, the locations where there is a strong variation, that property is quite nicely reflected by the final exponential mapping result. And as we have a discrepancy matrix for the exponentials, the final reconstruction results, we can also do the same type of discrepancy for the tangent vectors, and we get a very similar output for this phase data set. So now we take one of these subspaces UL with strong coupling, and we hope that the dimension is not too large. Not too large means 1, 2, 3, 4, 5 is already a little bit difficult. Then we consider a lattice in this space of weights for these basis vectors. And we explicitly compute a lookup table for these lattice tangent vectors and store them somewhere. And then we can, if we want to now compute an actual exponential in this subspace, we can just use multilinear combination of these lookup table exponential map values to compute an approximation of the exponential map for a given V vector. Now we just take these multilinear weights here and apply them to these exponentials from the lookup table. And then we join all this information from the different subspaces in linear fashion. We project them with a very few Gauss-Newton steps. And this is visualized here. So here is now this lookup table displayed, which is in has two base directions, mode A and mode C. So in magenta up here, you see these 1, 2, 3, these lookup table reconstructions. And with Latin 1, 2, 3, we see multilinear interpolations of these reconstructions. And if you look here for the point cloud on top, that's a perfect match. So there is almost no interpolation error. And you see with which dimensionality we work here. So we don't have too large resolutions of our lookup tables, because already low numbers of k give very good geodesics and thus very good exponential maps. And for the SCAPE data set, we have here 5 two-dimensional lookup tables, 6 three-dimensional ones, and 3 four-dimensional ones. And differently for the hands with 12, the faces with 10, the horses with 20 modes, we have these type of size of dimensionality of the subspaces, and therefore exponents used in the number of lookup table entries. And if we increase the number of clusters, for sure we reduce the number of basis factors in these clusters. That is shown here in the horse example. And the benefit is now that we basically have a lot of offline cost, but then very fast reconstruction algorithms online. So if you compare here a Catmull spline reconstruction, which requires 3 seconds in the classical PGA and only 60 milliseconds in the sparse PGA. Now, basically the cost is here these 1 or 2 back projection operations onto the manifold. That dominates basically this cost. And if we do human pose editing results, I will show in a second, then we see also a significant increase here from the PGA to the SPGA. And here you see the results for the mean computation, the log, and the solving of the quadratic programs and the exponential, and this z-tau evaluation. And the number of the amount of milliseconds per Gauss-Newton iteration, which usually is 1 to 4, is listed over here. So here is what you can do. You can do a Catmull-Clark spline interpolation. And it's important to do this back projection as the last step. Otherwise, we see very ugly artifacts here. This is without back projection here, and this is with this back projection. And here we see a difference between the PGA and the sparse PGA. Linear approximation quality for sure is best with PCA and PGA for sure. So this is this little gap between the sparse PGA and the PGA. L1 norms strongly drop if we increase this penalty factor, and we get fairly low L1 norms of the modes. And by the sparse approach, we are able to substantially reduce the overlap here compared to the PGA, with very strong overlap, with very moderate overlap. So now here we focus on mesh editing. So we have this horse model, and we want to do something very strange. We pull here at this leg here and have a constraint for this green position here. And if we do just linear interpolation, then this looks completely ugly. If we do editing with non-interpolation and hard constraints, it already looks substantially better. If we do editing with non-interpolation and soft constraints, it looks like this. So how is this editing done? So editing in the soft version is there is a penalty factor, and here's the discrepancy between the prescribed position and the actual position of our points. And then here's a regularization term, which involves our SPICE PGA result and compares the L theta variables for the X position vector with a preferred position on our manifold due to the SPICE mode with a variable U here reflecting the weights of the modes. And here you see this final result with our method. And here you see a comparison, which we already did for our old 2018 approach, which was rigid body motion invariant PGA. We start with this pose. We do at the green bullets an editing operation. And we see here quite some deformation results. The PGA leads to these results. Our method is 20 times faster and leads to these results, which are definitely comparable. And if we zoom, for instance, here into this, you see a much better 90-degree angle here and a much better forming of these muscles, and to see similar effects at different positions. And here you see our result in rotation to show the reconstruction. And for sure, that can be used for real-time animation purposes. This is a frame rate of about 20 frames per second. So we have seen that these new variables for the description of triangular surfaces, not the coordinates of the vertices, but the length of all the edges and the dihedral angles, they are a very handsome new coordinate system, which leads to an implicit description of the manifold of triangulations. And incorporating spicity, we obtain very localized separated modes. And these can be efficiently computed by alternating sequentially quadratic programming. And finally leads really with this lookup table approach to fast approximation scheme for nonlinear deformations, which is based on the superposition of modes, mode-based articulations. And with this, I would like to close my talk. Thanks for your attention.
Thank you very much. Perhaps we can thank the speaker. Okay, there are some questions. So the first is, do we understand correctly that for a PGA, all deformed triangular surface meshes must have the same mesh connectivity? Is there a way to react to slight changes in the mesh connectivity?
No. The answer for the first question is yes. These methods are all for the databases I've shown, which have fixed mesh topology. And the second question is currently, so we are thinking about this. We are thinking about this in an autoencoder setup. There are very first results, but that is not presentable at its current form. Yeah. So you really have to enter a completely new setup to treat this problem and to bridge between these principal component analysis and general mesh topology.
Okay. There's a related question, which is mesh coarsening is a heavily studied problem. Can this point of view help?
Sure, we heavily used mesh coarsening for our first methods, which were vertex-based. We tried out some edge collapsing algorithm to get an hierarchical approach in the L-theta space. That is far from trivial to turn into an effective approach. Huh?
Okay.
So actually, an efficient method is to coarse in the usual way, then to work on a coarse mesh first and do there the animation, then to prolongate onto the finer mesh and then restart that. So not a basically multi-scale approach, but a cascadic approach that works. And that is what we also used a couple of times.
Okay. At the start of the talk, there was the idea of using the energy to approximate the metric and do an approximate projection step. That seems like a very widely applicable kind of technique. Are there any other areas where this either has been used or do you think it might be a good strategy?
So this energy was an energy which discretizes basically a thin shell energy, because we think of our surfaces as being thin shells, discrete thin shells. If you think of imaging, then you can think of deformation energies, elastic energies of the volume. And then the Rayleigh paradigm turns these elastic energies, when you replace displacements by strain rates, into an energy representing viscous dissipation of the flow. And that's also a fairly good idea to be used to define a metric in the flow of diffeomorphism approach in imaging. And we have used this already extensively. So you can start with linearized elasticity or non-linearized elasticity energy, and you then configure a multipolar fluid model out of this, which is then the basis of the metric on the space of images.
So that's okay.
That answers the question.
I think it does. So there's a question which I think you may have just answered based on actually. So there's a lot of questions about interpolating between poses, and there's one question that says, if I just give you two poses and nothing else, can you get the geodesic between them?
Sure. If you have two poses, then you can compute for the Frisch mean of our SPICE PGA. You can compute a discrete geodesic between the Frisch mean and this object, and you can do this for both objects. And then you can project this onto the tangent space with these U modes, and then you can work with a different energy, with a similar energy than I used in the mesh editing to compute. In interpolation, it's easy to compute if we don't use the background input knowledge. Then you just compute a discrete geodesic. But if you want to use the probability of being at the right place in shape space from our SPGA, then you can use a similar regularization energy together with this K path energy to compute this this natural connection. We use this heavily in our approach, not in the results I presented, but we have examples for that.
I see. There's a question about, is there a good way of comparing this technique to other machine learning methods for interpolating between poses? So if I have...
We haven't compared with machine learning methods. We have compared extensively with other statistical methods. That you can also find in the associated paper, which was on one of the first slides. But we actually haven't so far in one of our papers compared to machine learning approaches.
So what kind of technique would you use? How would you compare it to a more statistical method? How would you decide which is best?
Hard to say, because our method takes its strength from this fixed topology. And most interpolation methods for machine learning avoid this constraint, like PointNet and PointNet++ and all these other nice techniques, which we partially also seen this week. And to make a fair comparison of our method, which strongly benefits from these topological restriction, I have no clue how to do it. Yeah.
Oh, so it's a slightly different problem.
Yeah, it's definitely an unfair comparison, I guess. Yeah, because our method works with a very strong restriction, which is reflected by many data sets, but which is typically not used in machine learning approaches. At least I'm not aware of one which works for fixed topology only. The machine learning challenge is really to have it flexible with respect to mesh topology.
Okay, thank you. And we have time for one more question, which is, does this analysis give insight into the geometry of the space of 3D shapes, especially when it comes to relating the same shape in different poses or at different resolutions?
Yes, to the first part of the question. So what is interesting to do is, I said this briefly, and we have a paper about this, one can compute with our discrete approach also remaining curvature tensors and sectional curvature. And sectional curvatures are a local description of the shape space at a certain position in the shape space. And you can, for instance, compute confusion matrices based on all the possible sectional curvatures for the dominant modes of shape variability. And these confusion matrices really tell you something about the strong coupling of modes and the local geometry of the shape space. And
okay,
particularly, you can, for instance, see that similar to this Mumford and Micho paper from about 15 years ago, they did this there for curves, and they could prove that the curvature of shape space with not too much geometric variation of the shape where we compute it is positive. So that means we are in elliptic local configuration. And if there are stronger spatial variations, then the sectional curvatures turn negative. And then we see that there is plenty of space in, if we are in a negative curve space, there is plenty of space in this shape space, so to say. So this is only a very partial answer for the second part of the question, but this is the only thing I can give you.
Thank you. I thought it was a very good answer. Okay, so let's thank the speaker again.
Thanks for the opportunity to present this.